in general, we can think of 5 different classifications for elasticity. Elasticity, we can think of there being 5 classifications. And we can see all of these different classifications on a linear demand curve. So let's draw out a demand curve and let's write out the formula and talk about it. All right, so we're going to draw this linear demand curve. Maybe it looks something like that. Here's our demand curve. We have our formula that we're going to rewrite. So remember, it's QD1 or QD2 minus QD1 or QD1 minus QD0 over the mean overall, like the percentage change in price using that midpoint method. Well, another way to express this fraction, we can take the denominator and flip it and multiply and kind of rearrange a bit. And so this is mathematically equivalent if we flip it. Oops, the 1 should be there, minus QD0 over P1 minus P0 times the average price over the average quantity demanded. These are mathematically the same. And this is going to be useful for thinking about what's happening as we're going to start at the top here and move our way down the curve. All right, so let's start at point A. Price and quantity. We're at this quantity 0. So we're using the midpoint method, so we're taking 2 points around 0, and we're calculating whose average is going to be 0, right? And this is 0. That means this quantity right here is a 0. So we're dividing, like the denominator is a 0, so we're dividing by 0. Well, here, elasticity is going to be equal to infinity. It's going to be infinite because we're dividing by 0. And then let's think about what happens as we move down. So, I mean, we're not dividing by 0 as soon as we're off this intercept here, but the price level is relatively large and the quantity is relatively small along kind of this first part of the curve away from A. So average price is big and average quantity is small. So as we move down, the prices is falling and the quantity is getting larger, but it's still, relatively large price to quantity. So there's going to be some portion of this curve where the elasticity is greater than 1. But it's falling as we move down, right? It's falling because the average price is decreasing as we move down this demand curve on this axis. And the quantity demanded, I should put a D here for quantity demanded. But the quantity demanded, the average of that is increasing as we move along. At some point, these two amounts are going to cancel each other out. That should be a 1, sorry. It's going to keep on falling until at some point along this curve, the elasticity is going to equal 1. So everything here is going to have to cancel out and we're going to get a 1. But it still keeps on falling as we continue to move down the curve. The average price is still falling. The average quantity is still rising as we move down this curve. And so there's going to be a portion here, so I was using green, where the elasticity is less than 1. And then finally, so use orange down here. And finally, this point here, the average price is 0. The numerator is 0. We're multiplying this part of the numerator by 0, so it's 0. And so at this point, eta equals 0. So here are 5 different classifications. We're going to write out these 5 different classifications, but here's kind of 5 different ranges of values for elasticity. So we're going to say that when eta, or elasticity equals infinity, that it's infinitely elastic. We're going to say that when eta is greater than 1 but less than infinity, we're going to call that just elastic. So here, a 1% change in price causes a greater than 1% decrease in quantity demanded. When it equals 1, we're going to say it's unit elastic. So at this point, a 1% increase in price causes a 1% drop in quantity demanded. If it's less than 1, we're going to call that inelastic. So a 1% increase in price causes a less than 1% decrease in quantity demanded. So buyers aren't that sensitive anymore to price. And then finally, when it's 0, it's going to be perfectly inelastic. I guess I should go back up here, and sometimes we say perfectly elastic. I guess I should have said perfectly elastic for eta equals infinity, but it's infinitely elastic as well. Okay, so even along this straight linear demand curve, we see the elasticity is changing as we move on it. So this is why I keep saying, relative elasticities, you can look at slopes maybe between two different demand curves, or supply and demand curve, as we'll see later with excise taxes. But even on one demand curve, the elasticity changes along it, except in a couple different cases. So let's draw a couple different curves where we have kind of constant elasticity. All right, so demand curves with constant elasticity. With constant elasticity. So we can draw a couple different curves here that, unlike a linear demand curve, have constant elasticity. So price and quantity on our axes, I guess it should be QD on this curve. And so if we have a perfectly vertical demand curve, for instance, this is going to be a perfectly inelastic demand curve. So D1 is perfectly inelastic. If you have a vertical demand curve, it means regardless of the price, the quantity demanded stays the same. Right? So buyers aren't sensitive to price at all. They need to buy it. So think about, some drug that you need to have to survive. People are going to be willing to pay whatever they can. Then we can think of the other extreme. We can think of this flat horizontal demand curve. Let's just call that D2. And this is going to be perfectly elastic. This pen is running out of ink a bit. Hopefully it comes through. So this is perfectly elastic. You raise the price by just a tiny bit, quantity demanded goes to 0. And then we could think of, a curve where it's unit elastic the whole time. And it would have to look something like this. So at all these points along this curve, the elasticity is going to be equal to 1. So here are 3 different curves with constant elasticity. A vertical demand curve is perfectly inelastic. A horizontal demand curve is perfectly elastic. And we can think of a unit elastic demand curve, which kind of has this non-linear shape to it.